Let's begin our discussion on the assignment problem. In fact, assignment problem is a special case of linear programming problem, but it has got its commonality with the transportation problem, but it is little different from transportation problem as well, right? So in a transportation problem, we have got n source and m destinations, and we could able to allocate even multiple destinations from a single source, but that is not possible in assignment problem. In an assignment problem, the assumption is that will be only giving individual job to an individual person, so which means a source goes to only a particular destination. So that's as simple as that, right? So this has got many real-time examples. Say for example, if you wanted to choose a network, a mobile network, then you could probably choose from a lot of different networks, communication agencies, right? So you cannot have all, or you can have multiple communications for a single sim or something. So that's what basically it means, like you could only allocate one thing to one person. So as simple as that. So those are examples of assignment problems, and here's one example. Before we get into the theoretical part of what is assignment problem, let's take a look at the some good examples so that you understand what is assignment problem in detail, right? And this is typically typesetting or printing a thesis or some report or something like that, right? So these are the jobs, like, or the task. Like one is typesetting, who typesets that, which means like typing the documents. And J2 is cover page design, so who does the cover page design. And J3 is printing, and J4 is binding, right? So it's all a complete task, right? So each and everything is an individual entity so as to complete a task or a project or something like that, right? And these are the shops, like who uh, these are the shops that performs these all four things, right? Something like that. And one of the important things about assignment problems are assignment problems should be a square matrix. So for example, in a transportation problem, we have got four destinations and three sources, whereas you can even have two destinations and six sources and something like that. And that's a very valid thing in a transportation problem, but that's not possible in an assignment problem. Say the assignment problems I told you, we need to allocate one job to one person, so which means that it should have got destinations equals to the source, so which means that it should have got input equals to the output, or probably like the allocations, right? So it should be a square matrix. It could be 3 by 3, it could be 4 by 3, it could be 5 by 5. I'm sorry, 4 by 4 and 5 by 5, but it can't be a skewed matrix, or it cannot have any other non-square matrix, right? Something like that. Say even here, you take a look at this. We have got job 1 to 4, so which means we have got four rows, and we also have got four columns, like shop 1, shop 2, shop 3, and shop 4, right? Sometimes we may get skewed matrix, but that is basically called unbalanced assignment problems. So we have some procedure to rectify that, so that we will be taking a look at that probably tomorrow session or day after tomorrow session, right? Somewhere, right? Let's take a look at what these things can offer. Like, so these are the cost in terms of performing the task. Like for example, this is rupees 75, which is like for typesetting. It's a job one. The shop one gets expects rupees 75, whereas the shop two, they charge 80 rupees, and charge three, it's probably 110, which is pretty higher, and shop four, that is 90 rupees or something like that, right? So as a layman, you will not interested in paying higher price when there is another option available, right? So let's assume that these shops are in the same complex, so you don't have to travel to a different place where it adds additional transportation cost. So all the shops are available in the same complex, and you want to perform this, and you will be choosing typesetting from a place where it is lesser, like where the charge less, or something like that. Say if you arbitrarily look, like 75 is less than of all these things, I guess 80, 110, 90, out of this 75 is lesser. So you might give job 1 to worker 1, right? Something like that. But once you allocate one, say for example this job to this worker, you cannot allocate other jobs to the same worker. Say talk about machine that produces some fabrication, that does fabrication and produces some finished product. So you cannot allocate when the machine is in operation, right? So we have to wait till the end of that machine, I mean end of the process, or the output of the raw material is achieved. So till then you have to wait, then only you can allocate. Similarly, like you cannot allocate once you give a job to a particular worker or something like that, right? So that's basically what it means, right? Something, right? So sometimes you can even incorporate time factors into it. uh, when you remove cost, you can even add time, so you can find quickest time by allocating two different shops, so that the process, the work gets done early, right? So this is a typically a nostalgic experience, like when we do a master's degree, we need to take a printout like thesis. Like in some shops, like I studied in College of Engineering Gindi. Adyar is nearby, so we used to go to Adyar students' rocks, and then we print our manuscript or the thesis. But the thing is that in an abstract, we need to have Tamil typeset abstract in addition to English. So only the abstract being an additional thing. I mean, Tamil being added in the abstract. So we need to find a typesetter who can typeset Tamil. Like some people who are really good in typesetting Tamil, they can bring that and they can print it pretty easily. But people who have got difficulty, they have to find a shop who typesets this. Like generally, there is a shop in Tirvanmur, which is next to Adyar. They does the Tamil typesetting, and when you dictate them, then they do it something like that, right? So, but if you have already written or typesetted by yourself, then it's pretty easy. You just only have to find a shop that's printed, like so you can give it to any shop that prints that, right? Something. So that's basically what I'm gonna try to say here is like that's how this cost might be. Like typesetting, it's just like a printed thing, or in this case it's typeset the work required by the person as also the printing charges, something like that. So that's how this charges are, like it's pretty much a very very important thing. And then this is the given problem, and this is from this we will be finding out these solution, right? Something. First thing is like you make up this particular assignment tableau, and the same question gets given here. Or sometimes in exam we'll give only shop 1, shop 2. You can give any nomenclature, S1, S2. It does not makes any difference, right? So then job or worker, this is worker actually, this is job, and something like that. And finally this will be our assignment tableau. In addition to the given problem, we have to find row minimum as well as column minimum. Remember in Vogel's approximation method, we talked about the penalty, right? So penalty cost, which is the second least minus the first least, something like that, right? So in here, we'll be taking the entire row and we will be finding out the minimum of that, right? So in this case, this row J1 row, it is 75, 80, 110 and 90. Among this, the minimum is 75, right? So let's also do that for row 2, which is 120, 90, 100 and 80. So among this, the least is 80, right? So since I do it in Excel, so I can find with a minimum of these things. But sometimes in exam, you might do it in a hurry. So when you look at this thing, like you might say 90 is the least. So when you substitute 90, then the entire problem can go wrong. So kindly make sure that you read all the elements and find out which is minimum, right? And in this case 80, 75, 85, 90. And if there is a tie also, you can select that if there is a tie between the and among the least numbers, you can take that. So that does not make any significance, right? So least is a least. So this is the for overall least in the row. So in this row, it is 110, 130, 80, and 120. Among this, the least is 80. So we'll put that 80 here. And this is the row minimum. And same way, we have to perform column minimum. So in column wise, we need to find which one is minimum, right? So in this case is 75 and 120, 80 and 110. Among this, the least is 75, right? And then when we move to the next column, which has got 80, 90, 75 and 130, you see the 75 is the least, right? And then when you come back to this thing, the third column, which is 110, 100, 85 and 80. So among this, the least is 80. And if you take a look at the fourth column, out of 90, 80, 90 and 120, the least is the 80. So this is a typically column minimum, right? So we have found out row minimum, row wise, which is minimum, and column minimum, column wise, which is minimum. In fact, we'll take the least of all. I mean, least in the row, every rows we'll find out the least cost, and column wise we'll find out the least cost, and we'll tabulate here, right? So now we will be doing elementary row operation, which is the row reduction. First, what we do is we take this thing, use of row minimum. Remember, you should not perform column minimum before a row minimum. I mean, column wise reduction before row wise reduction. First is row wise reduction. So what we're gonna do is, like, this is our least value. Like, we will be subtracting this least value among these rows. Like, for example, 75 minus 75 will become 0. 75 minus 75 is 0. And 80 minus 75 is 5. And 110 minus 75 is 35. And 90 minus 75 is 15, and something like that. And you have to perform for entire thing, right? So entire row. Once you perform entire row, we will get 0, because we will be subtracting that number by the least number. This is the least number, which is an element in the particular set, no? So that will become 0. So 75 minus 75 will become 0. 80 minus 80 will become 0. 75 minus 75 will become 0. 80 minus 80 will become 0. And finally, after that also, you have to find row minimum, right? So generally it will be 0. Once you perform the elementary row operation, it will be 0. So once you perform elementary row operation, which means a row wise reduction, which means that you are removing that particular smaller number by subtracting to the same smaller number. So you'll definitely get 0, and finally all the row minimums are 0, right? This is true for column minimum also, right? So we have just performed row reduction, and then you can check whether the column has got a minimum, something like that, right? So luckily in this case, we have got column wise also 0, 0 here and 0 here and 0 here and 0. So which means that all the columns have got 0. So this is a typical case. Generally in column minimum will have some values, some columns will not have 0. So that we will be taking a look at that in example number 2. But in this example, luckily we have got all the elements in the column minimum is 0, and we also need to verify that. So when we perform row wise, column wise reduction, so next step will be column wise reduction, when which the minimum here, it is the minimum value of the column is 0, this column is 0, and this column is 0, and this column is 0, and whatever you do, like 0 minus 0 is 0, 40 minus 0 is 40, 5 minus 0 is 0, 30 minus 0 is 0. So which means that it will be the same matrix. So unfortunately in column wise reduction, there isn't any effect, or there's no change in the thing, right? Something else. Next will be this will be the 50% of the problem. So first we have taken this and we found row minimum and column minimum. Then we will be performing row wise reduction. You can even call this to be step 2. So this will be step 1, and this will be step 3, and this will be step 4. So only 4 steps. First we'll perform the row minimum, then column minimum, then row wise reduction, then column wise reduction, and after that, that matrix, this thing is used for finding out the optimality matrix, right? So we will be first initially looking at the the locations of the zeros. Like for example, in the first row, where does the zero comes? Here it is. So we will mark that. And in the next row, where does the zero comes? Here it is. Yeah, we will be marking that. And in the third row, we'll be looking at the zeros location. Here it is. And in the fourth row, let's take a look at where is the zeros, and here it is. Like, and we mark that. So which means that 1, 2, 3, 4. So which means that we had, this is just a step 1, step 4a. There's another thing you should really look into, which is the step 4b. Luckily, in this case, we don't have much of that implication. Like, let's take a look at that. Right. So once you do allocations, like say for example, when you mark all the zeros, and make sure that the next step 4b will be, we'll go back to this zero. I mean, yeah, we'll go back to this zero, such a way that when you take first allocation, make sure that there isn't any other allocation in that particular row and particular column. So I mean, if this is a distinct zero and it does not have any other zeros in the rows and columns, in that corresponding rows and columns, right? Say we don't have any zero here and we don't have any zero here. So which means that this is okay. So we have done a best job of allocating, right? Now let's take a look at the second row, which has got its zero here, and there isn't any zero here. And is there any zero here? No, absolutely no. So which means that we have allocated a perfect zero here, right? Next, we'll come back to the third row. We'll look into the row wise if there is any zero. So it's only distinct zero. There isn't any other zero. So zero represents the allocations, right? So remember, we do all the processes to end up with zero, so that zero is allocated to that. That's something we'll take a look at that a little later. But in this row, third row, we don't have any other zeros left. So I'm gonna remove these things so that we'll go back to the third row. Yeah, in the third row, we don't have any zeros in the row wise as well as in the column wise. So which means that we have perfectly allocated, right? Say, take a look at this. There isn't any zeros that is intersecting in the row or in column. So which means this is a perfect allocation. And very important thing is that, let's take a look at that. So we need to find a number of allocations, right? So in this case, the number of allocations is 1, 2, 3, and 4, right? So we have got 4 allocations, and the number of desired allocations. Let's take a look at the number of desired allocations is that for a 4 by 4 for a 4 by this is just a 4 by 4 matrix, so which means that we need to have 4 allocations, right? Say it's the difference is 0, then we have perfectly allocated. So which means that the number of allocations is 4, and the desired allocations is also 4. The desired allocations is that, like, we need to have 4 jobs assigned to 4 workers. So it's a 4 by 4 matrix. So that's why we have desired allocations to be 4, right? Right. And number of allocations actually 1, 2, 3, and 4, something like that. So that's 4, and hence it is fine, right? So why do we have this thing is that, so that's a corresponding allocation. So J1 is allocated to W1, and J2 is allocated to W4, and J3 is allocated to W2, and J4 is allocated to W3. So that's how it is. And when we go back to the original table, I'll copy this for a moment. And when you provided, like J, this is 75, so I'm gonna 75, and then this is 80. Take a look at that as 80, and the third is this W2, which is 75, 75, and this is 80, right? Something like that. This is 80. So you see, even in a theoretical perspective, we can see that 75 is less than 80 in something like that, and 120, 90, and 100 among this 80 is lesser, and among this 75 is lesser, and among this 80 is lesser. So which means that when you allocate job J1 W1 to be 75, J2 W4 is 80, J3 W2 is 75, and J4 W3 is 80. So which means that we'll get 310 rupees as a whole, and individual jobs is this something like that. Fine. But if you allocate it by other means, you will get maximum value only, more than this, but never less than this. So that's basically the optimal matrix, or optimality is reached, something like that. So this is a simple problem in which we looked into all those things like allocations by row reduction and column reduction, and we performed the optimality matrix and something like that. But sometimes we will not get deliberately like this. The assignment problems will not be thus kind of pretty easy. Instead, we'll have a lot of other confusions. Like there will be other zeros, other allocations in the same row itself. So let's take a look at how to avoid those, or how to eliminate those to us to find out the optimal matrix, right? So the procedure we're gonna find is called Hungarian algorithm. So it's a very important algorithm for solving assignment problems. Let's take a look at that. So this is an assignment problem. I can even put it like Hungarian algorithm. As the people who developed this are from Hungary, so they have named it as Hungarian algorithm, right? So this is not the same problem. This is a different problem. Maybe a mechanical engineering problem or a manufacturing problem. Like the task one is procuring raw materials, and job two is fabricating that, and job three is assembling that fabricated stuff, and job four is finishing or painting. So this is typically a mechanical engineering or production sectors problem, and it has got shop 1, 2, 3, and 4. So you can perform this among this four shops, or warehouse, or the manufacturing yard, or something like that, right? Right. So once this is done, so the next step is finding out the row minimum and column minimum, right? So we'll copy the same thing, and we'll perform row minimum and column minimum. Row minimum is the minimum of the row, that is here 13 is 13, and among this is 15 is the lowest, so 15, and so on. And column wise, we have got 20, 15, 40, and 21. Among that, the minimum is 15, so we end up with 15 here, right? And similarly, find out column minimum for the other two columns, like W2, W3, and W4, and that will be a little bit the same process what we have carried out in the previous example, right? Now let's perform row wise reduction, right? So 13 gets minused from all the other elements, like 20 minus 13, 28 minus 13, 19 minus 13, and 13 minus 13. So which means that this is the value. And finally, you can see that the row minimum, all the row minimums are 0, because there will be one, you'll be subtracting the same value, same least value. So all the rows will have one least value, and when you subtract by the same number, you'll get 0, right? But if you take a look at the column minimum, so once you perform row wise reduction, you also check for column minimum. So I repeat, so once you perform row wise reduction, you also have to perform column minimum, right? So in this case, here we have a prominent 0, but if you see here, we don't have any 0 at all in this column. But if we take a look at this row wise, we have got one zeros in each row. But if you take a column wise, you see there isn't any uh, 0 here. So instead we have got 4 as a minimum, and same way when you take a look at here, we have got 3 as minimum, and finally this row, it has got a many zeros, so 0 is the minimum, right? So then you have to perform column wise reduction. In the column wise reduction, we'll be subtracting the least value from the column minimum, right? So in this case is 0. So 0 minus 0 is 0, and even 7 minus 0 is also 7. 23 minus 0 is also 23. So the number retains. So the column, the entries in the column retain, since we are minusing with 0, right? And in this case, if you take a look at this, we have got a minimum, column minimum to be 4. So which means that 15 minus 4 is 11. Another 15 is there, minus 4 is 11. And 4 minus 4 is 0. And 16 minus 4 is 12, and so on, right? So in this case, we have got the least value to be 3. So 3 minus 3 is 0, whereas the rest of the elements has some value, like 6 minus 3 is 6, 3. 16 minus 3 is 13, and 14 minus 3 is 11. So we have got this. And finally, the last case, we have got only 0. So 0 minusing 0 from any number will yield the same number. So that's as simple as that. So after this, if you take a look at the, if you remember the previous problem, after this we'll be finding out the optimality matrix. Like say for example, we will simply run through this row and we'll mark the 0. So in this case, we marked it 0, and we'll simply run through the next row and we'll mark 0 here and 0 here. And when we come back to the third, it's really a surprising element. Like for example, I might mark it 0, 0, 0. And when I come to the third row, there's a surprise. There's a 3 zeros, right? So you cannot afford to choose all the zeros. The rule says that we will be taking it only 1 0, which means that's a perfect allocation. And then we will be taking it for granted for allocation. But since we have got these zeros also comes into picture, and another important thing is that there is a 0 already allocated in that particular column, so that's an extra 0 here. So which means that we select this, we assume that we allocate to this, but we will discard these zeros. I repeat. So the first 0 encounter which we allocate, we will be marking it with, we will selecting that, and we will discard the other 0. So we try to do an algorithm so that we can eliminate these kind of pitfalls. That's called Hungarian algorithm. But in the initial stage, your process should be select the 0, and if there's have any other zeros in that particular row, you will mark it, make sure that you don't delete that. So you keep that, and you just since in an Excel I marked it with color, so in real practice you can mark it with circle or something like that with your pen, right? Then we'll come back to the fourth row, and when you come back to the fourth row, so you can even see that there is a 0 already allocated, and then we cannot allocate this 0 in that particular row since the column itself has got a 0 there, right? So which means that the basic objective of assignment problem is to find out the distinct allocations or distinct 0, right? Something like that, right? In this case, the number of allocations, it's a 4 by 4 matrix. So the number of desired allocation is 4, whereas the number of actual allocation is 3. So 1, 2, and 3. So this is the distinct allocation, 1, 2, and 3. So this is 3 is less than 4, right? So now it is not optimal or not optimal, right? So now is a very important thing. All of you kindly pay attention, because Hungarian algorithm is a very, very important thing, and you should know to solve any assignment problems. And also it is a little confusing because it has got a lot of steps to remember. Like if you take any NPTEL video, they have got a very comprehensive and kind of a very different way they perform Hungarian algorithm. But I have from my experience, I have altered some things so that it is pretty easy, because in any lecture, any books, textbooks you see in Hungarian algorithm, they have got only tick mark and X mark, and it will be very confusing. You provide tick to 2 intersection, you provide tick to 1 intersection, and all will be pretty much confusing, right? So what I have done on my own is to simplified this Hungarian algorithm, and also I have made such a way that these steps are not confusing as the other lectures or other stuffs in the books. So it is just designed a little bit different, right? So that's why you can even learn that particular process, but the end result will be the same. but just to give you a clear idea what this Hungarian algorithm is all about, right? So the procedure is that first put an X mark next to the unassigned row. So this is very important. So we'll take this particular not optimal allocations, and then we'll be working on it to make it more optimal, right? So I repeat. So if you find it not optimal, then we will be incorporating Hungarian algorithm to make it optimal, right? So the process goes like that. First, you'll put an X mark next to an unassigned row. So this is a row which has an assignment here, and in this row there's an assignment here, and in this row also there's an assignment here. Despite two unallocations, we have got an allocated 0 here, and this row has got only one which is also barred, which is not taken into consideration. Hence, we can put an X mark next to an unassigned row. So in this row we have not put any assignment at all. Why? So that's very important, right? Now put y in the column corresponding to the x if the column contains 0, right? So what I'm going to do is I'm going to, I'll just, for a moment, I'll just isolate this particular thing. I have isolated that. Let me in this thing, what I'm going to do is I'm going to scan this row, and I'm gonna put y underneath the column. So this one column, two column, three column, and four column underneath the column which has got a 0. So in this case, we have got a column which has got a 0 value, and underneath that I put y. Right. So that's what it means, that put y in the column corresponding to the x, which means this row, and if the column contains 0. So if there's a 0 here, I'll put y, right, something like that. Right. Now put z in the row corresponding to the y column if the column contains an assigned 0, right? So now this is little trickier. I have to move here, and I'll take up this particular thing, right? So now what I basically do is I'm gonna put z such a way that among the y column which has got the assigned 0. So in the y column the assigned 0 is here, so I'll put z corresponding to that particular row, right? So I repeat, first I have taken this x. How do we take this? Is unassigned rows is x, then among the unassigned row the place of occurrence of y, I mean place of occurrence of 0, I put y. Then that column is selected, and among that if there is any allocation, in that case I put z corresponding to that, right? So that's how I make it x, y, z. In some lectures they'll say with a tick tick tick, so you might confuse that. So I've got a different nomenclature that will be pretty useful for you, right? So once you've done z, this is a very interesting step. Now what you have to do is draw lines through unlabeled rows and labeled columns. Remember, unlabeled rows and labeled columns. So which means that these things are labeled. So this is labeled. So which means that we have to run through unlabeled rows. Where does the label does not have? Like here is that, and here is that. So unlabeled rows and labeled columns. Say here is a labeled column y. So if we run through it, something like that, right? So that's how it is. Unlabeled row. So you see there's no label here. There's no label here, but there's a label here, right? So that's basically a very important thing that you should perform, right? And if you see the number of lines represent number of possible assignment, right? Say we have got 3 lines, like 1, 2, 3. So that's can be modification can be happen based on this 3 lines, something like that, right? So next step is very important. We will be finding out the smallest number in the cell that is not allocated or line drawn through it, like something like, in this case these are the cells like 7, 11, 13. I'll just isolate that for you. 7, 11, 13, which is having no allocation, as well as the no numbers, no lines passing through that, right? So the Hungarian algorithm is like that. It's a little tricky. So understand it perfectly. So among this, which has the minimum value? So 3 is the minimum value. So we select 3, right? So I repeat, it is little confusing. So I'll just do it from the scratch. So the first step is we'll find an unallocated row, which we'll mark it with X. And among the row, we'll be finding out the 0 value, and corresponding to that particular column, we'll mark it Y. Say for example, if you have zeros and other things also, you'll be marking it with Y, right? So it's not, in this case, luckily we have got only 1 0. So we mark it with only 1 Y. In case sometimes you might end up with rows having 2 or more zeros, so you have to correspondingly provide the Y, right? So when you provide Y, then next step is providing Z. So how do we provide Z? Is that in the Y column which has the allocated 0. So in that case is 0 here, so we'll mark it with Z here, right? Then we will be marking lines. We will be striking kind of lines, that is unlabeled rows. So the rows, this row is not labeled. These are the labels. So it does not have anything, no? So it's empty. In an empty stuff, we will be running through the line, and in labeled column, like remember unlabeled rows and labeled columns. So here it is labeled. So we'll run through this, and if you see, this is how it is, right? And then what we do is we will be taking the values which is not cut by the line, uh, and not allocated. So if there is a 0 and if it is green, you don't have to take that. So instead, any other elements, any other values is there, then you will be taking that particular thing, and among that you have to find a least value. So this case is 3. So which means we'll be considering that to be uh, small x. Remember, this is different from the label. In a label, you can provide capital X. In this thing, you can provide small x, or you can even call this to be small a. This matter. So just an differentiation, right? Say this is 3, and the smallest number is 3, and then what you do is you subtract 3 in the cell that is not allocated or lines joined. So which means that we'll be removing this with the minusing that with the 3, and similarly I'll have this 11. I think it should be 11 minus 3 or something like that, or it could be 3 minus 3, 3 minus 3, and this will be 9 minus 3, and this will be 12 minus 3, and this will be 11 minus 3, right? Something like that. So now we have got this thing, right? So something like that. And then the next step will be, this is a, I can even call this a equals to 3, right? So we have subtracted 3, and we have provide this. You can see 7, I think it's 7 minus 3. Yes. Like we have got 4, 8, 0, and 6, 9, and 8. So that's basically that. The next step is pretty much important. We have to add 3 to the number in the cell that has got 2 lines passing through them. Like for example, among this case, which cell has got 2 lines passing through it? Like in this case, it's only 1 line. In this case, is also 1 line, and in this case, 1 line, 1 line, 1 line, 1 line, 1 line, and 1 line. But if you take a look at this 2 cells, which is 16 and 3, it is actually 13 and 0. So here it is. So this is the place where we have got 2 lines passing through, right? So in this case, what we have to do is we have to take that particular value and add 3, which is our least value. So a is 3, so we have to add 3 to it. Then similarly, this 0 plus 3, that will become 3. So it'll be no more 0 here, so or unallocated 0, something like that. So which means that this will become 16 and this will become 3, right? So which means that once you finish that, you can eliminate this particular thing, and let's take, I'll copy this. Right, now what we do is after this step we will be you can use pencils to do an exam so that we can remove this. Now this is pretty much an different allocations now, right? Remember this has 0 has comes into picture, and these are the two allocations when which one gets changed to a number. So we'll end up with this, and this is the end result of an Hungarian algorithm. Next step, what you do is you do a row scanning. In the first instant, we have got 4, 8, and 0. So this will become our first 0. So which means that just I'll format it. Right. So once you come back to this and you remove the next 0, so which means it's not into consideration. And then we'll come back to the next row. So among this row, and we have got only one 0, so it's fine, fair enough. Go to the third row, and in the first instance we have got 0 and 0 here. Remember when we select this 0, this 0 is barred, this is barred, and luckily we have got another 0 in the column, so this is an optimal thing, right? So that's a basic thing. And next step, when you come back to the fourth row, there is a 0 here and there isn't any 0 which is allocated, so which means that this is allocated, so which means that remove all these things. So which means that we have got 4 allocations now. So the number of allocations is 4 and the number of desired outcomes is 4, then hence it is 0. So which means that we are perfectly allocated. So the assignment problem is over. And check that this column and this row does not have any other zeros, only this zeros. This is discarded. If you want, you can remove that. Like there's no 0. So I put X. I can remove all the things and you can see. Now you can see there's a distinct 0 in the row and distinct 0 in the column, distinct 0 in this row and distinct 0 in the column, and distinct 0 in this row and distinct 0 in this column, and so as the fourth one. So which means that job 1 is allocated to W3, so which means it's done, and job 2 is allocated to W1, is done, and job 3 is allocated to W2 is also done, and job 4 is only left with W4 and it's done, and it's perfectly allocated. All jobs gets perfectly allocated, and finally it is optimum. Number of actual allocations equals to number of desired allocations, and it is optimum, right? And then the costs are given here, like W3, J1 is W3, say the J1 is W3 is 19, and J2 is W1 is 15, it's just 15, and so on, right? And J4 is W4, it's just 12, and something like that, right? Let's take a look at that in detail, because that's one significant thing that you should know. Do not blindly state whichever is minimum. So in this case, you see, even though we have 13 for J1, which is minimum, but we choose 19 because if you choose 13, the other allocation may not be possible, right? So that's how J4 cannot be allocated with this 12. So that's why we select this thing. But if you do it, give blue. So this one is 13. This is taken, right? So we cannot allocate anything to it. And any columns is also barred, right? So we have allocated the job. Now in J2 minimum is here, so we cannot allocate anything to it. And in J3 we can allocate 20 because we have not done here, so this is 20. And J4 we cannot allocate here because we only will be ending up at only 28, not 21, because it's already allocated. Say this is 18 or something like that. we'll just have to just remove this stuffs to avoid confusion, right? Now our allocations will be, possible allocations will be 13 plus 15 plus 20 plus 28. So it's not even 2 rupees, it's kind of a 9 rupee extra. So that's basically by layman's perspective, right? So that's it. Like, we have come to the end of this lecture today.